All right, gang, Math 6610. Really going to put everything that we've done so far, put it to work. And I have to be in complete transparency. I've served on 15 doctoral advisory committees. I think at this point I've had 92 master's theses advisees. I have never seen a one sample t-test presented in research, any of the research projects. But again, I think it just serves as a good place to begin because what we'll do is we'll take this into independent samples t-test and dependent samples t-test and ultimately chi-square and ANOVA, techniques that I have seen done in research leading up to the larger research question. So I'm just going to demonstrate, over here, I have a data set. I think we've looked at it before. It's called Admit GRE. So you can see it, I already have this imported into R. And I want to pump the brakes a little bit and tell you that I'm using R, and you can see it's version 3.6.3. Kind of a strange something that I'll admit, when I am conducting statistical analysis on my own, I use RStudio. But when I'm teaching, I use R. So you may consider diving into RStudio. It has a lot of advantages. I don't know why I don't use it to teach. It's just you can't teach an old dog new tricks. I've become comfortable teaching with R, the base version. But when I conduct the analysis, my analyses on my own, I use RStudio. So just throwing it out there. If you want to examine that, go for it. So if I were reporting this in the literature, or I'm sorry, reporting this in a study, first thing I would do, and I'm gonna show you how I find all these calculations. Okay, so first thing I would introduce is just what study or what statistical technique that I've used. And I can say that I used a one sample t-test to examine that the mean GRE at a large university is different than 600, which represents the mean GRE for the population. The next thing I would do is I would use G-power to conduct a priori power analysis. Well, I have G-power up, and let me show you how I would do this. So first thing I would do is I would go to the test family, and I know that I'm going to be conducting a t-test because we're again assuming that the population standard deviation isn't known. Next thing I would do is come down and find the entry that applies to what I'm doing. So it's just a difference from a constant in one sample case. And the next thing I would do is a priori. Now, the other one that you use sometime is called a post hoc, where you compute the power, or you calculate the power analysis based on the sample size given. So there's a lot of controversy surrounding post hoc power analyses. I see nothing wrong with them as long as they're interpreted with a bit of caution. So we're going to run a priori, and you can see the inputs that we need. First of all, we're running a two-tail. I would always recommend a two-tail test for a single test or even independent or dependent samples, which we'll talk about later. The effect size turns out to be 0.1065. Now, the effect size for a one sample t-test is just, we just use Cohen's d. And it's, let me use a hashtag here so I can communicate to you. It's just the x bar minus mu divided by the standard deviation. So it's very, very easy to calculate. So the first thing I would need, I would need the mean for GRE, and I would need the standard deviation for GRE. So the effect size is just going to be the mean for GRE minus the claim divided by the standard deviation for GRE. So our effect size, when we just look at the absolute value of this, would be 0.107. So I'm going to put 0.10, well, I'll put 0.1065 there. We're testing at 0.05 for the alpha level, and I want my desired power to be 0.8. So when I hit calculate, you can see that the total sample size needed to achieve a power of 0.80 is 694. So in complete transparency and reporting my results, first of all, I state the program used to calculate the power. And the next thing I do is I report that we need a sample size of 694. In complete transparency, I say that adequate power may be a concern because this analysis was used, or at least 400 was with the sample size of 400. And you can see over here, this is where I calculated the sample size. All right. Next thing I did is, again, the first thing I want to do is just look at my sample, these 400 students. And I can see the two outliers emerged. That's the primary reason for reporting a box plot. And this histogram of the GREs looks relatively bell-shaped and symmetric. Don't ever tattoo this into the brain. I will take off major points if you call that a normal distribution. Normal distributions are theoretical distributions. They represent populations. This is not a population. This is 400 students who were as our sample. So we can talk about skewed, right skewed, left skewed. We can talk about bell-shaped and symmetric. Normal distribution is not appropriate for describing a sample. It's a theoretical probability or population description. Next thing I do is I get into the statement. So GREs from the sample reported significantly. So that tells me that I have a significant result, lower GRE scores. So I report my mean at 587.70. I report my standard deviations, 115.52. Again, information I got over here. That's why I calculated this and not just the effect size. Why is that population? Okay. Then the population as a whole. So the first thing I do is I calculate, or I report the letter of the test. I report the letter of the sampling distribution that we've talked about ad nauseum. I used a t-test here, so I'm going to start with the letter T. The next thing I report are the degrees of freedom, and then I report the test statistic and the p-value. So finding that stuff in R is very simple. Just t-test. I want GRE. I want to test that the mean is equal to 600, and I want the confidence level equal to 0.95. I don't think that's needed because I think the default is 0.95, but I'll put it in there anyway. So you can see the degrees of freedom from the output, the test statistic from the output, and remember a previous video we talked about reporting p-values. This value is less, this p-value is less than 0.05, but not less than 0.01. So it falls into the range of where we would report as p less than 0.05. I'm going to ding you guys on your assignments if you do not report p-values correctly. For example, if you report this as 0.034 or 33, whatever, I'm going to take off because that's not the way we report p-values in research. Next thing I did is I reported the 95% confidence interval, again coming from the output. And then I said the difference in the sample and the population mean represented a small effect size, small sized effect of 1.1065. Now, one thing I want you to do to make sure that you report digits consistently If you report the mean and the standard deviation to 2 places beyond the decimal point, be consistent with that. Effect size probably should be consistent with that, actually, and report D equal 0.11. I like 2 places. I think it gives enough information without getting messy. But I think a few APA, Chicago, ML, I'm not sure. I think they recommend 2 places on this, but I'd have to look that up to be sure. So that's what we do. Compact, yet there's a lot of punch in these 2 paragraphs. So that's all I got. Take care.